delay because we had some technical glitch. So that's why we are delayed also a little bit by 10-15 minutes. So yeah, so let us get started. So in the last class, what we had seen where in the standpoint or from the standpoint of SOMs, we had seen that an overview of SOMs, so how you can look at soft oxometalates and SOMs. Then we had come to the aspect of patterning with SOMs, how you can do patterning, and that we talked about microbubble lithography and so on. And today we will be talking about soft oxometalates in catalysis. And this is going quite nicely because, as you have seen in the morning class, Kari has been developing step by step with very basic concepts of crystallography, so which is really augmenting the aspect of these type of materials which are beyond this translational periodicity. And these are soft matter systems, and as we have said that with these soft matter systems you have lot of advantages over the systems that have certain rigidity. Now here in these type of systems we have the violation or not the necessity of translational periodicity. So you have these colloidal entities which are beyond the translational periodicity, which is quite nice in a way that you can form structures beyond translational periodicity as and when you want. So we will highlight only the aspects of catalysis, and as I mentioned to you earlier, so all this work has been possible because of this excellent group that we have at IISER Kolkata, and they are in the background as well with this program today. So now let us get started. So if you see, for example, this is active matter. So this is the matter that moves. It really moves in real time. And what I will show you today, unlike yesterday where we had, on Friday where we had seen that how you have this translational periodicity and how you had the motion of these particles under different conditions. Today I will show you the motion of these particles under optical field, and you will see that they move and you can control their motion with optical field. Patterning I have already talked about, so I am not going to talk about it today. So we will show you also some of these reactions which we have seen where we harvest the structural versatility of the soft oxometalates with these type of reactions. So, and I will go a little bit so instead of just focusing on the products and the yields, we will look at the mechanistic pathways for these type of CO2 reducing systems as well. So you can see, for example, this motion of the particle that was moving. So again, the basic framework, I'll repeat. So this is the basic framework which we follow. So we keep energy in the center, then you have the assembly and the disassembly. You can use it for partition. So we will not talk about partitioning. We will today talk about reaction and a bit about the motion, and then this assembly, disassembly, how it works. So last class I had talked about how these assembly, disassembly systems can be harvested for creating motion. So today you will see it's more driven by the phoretic effects and how you see the changes in the reaction systems and how you have this motion. So let us get started. This was a work that was done by Opabrita Mollik in my lab, and so what she did was quite fantastic. She started with titanium nanoparticles, so titanium dioxide nanoparticles, and then with this titanium dioxide she put on it MO7 type systems. so that she gets titanium MO7 type SOX. And then she irradiated them for 6 hours and then put gold chloride and paired finally this composite with titania MO7 and gold. Now you will realize it. So these have 3 components. So the titania is the photoactive component, MO7 is the redox component, and gold is augmenting in the reactivity component. So these are the 3 components which were built in the system and which does the reaction in there. So what happens there is the following. So you have this particle and you have the band edges. So meaning these are like optical semiconductors, right? So that means they have a certain band gap, and in the band edges, 2 band edges, you can do 2 different types of reactions. On one edge, you can create basically with the harvesting of the light, you can differentiate the holes and the excitons, and we have referred to it in the last class. So the holes essentially split the water and then creates oxygen, and the electrons are then transmitted so into the gold nanoparticle. Now because of this production of oxygen, there is a certain slip velocity that is created, meaning that there is a certain difference in the speed with which the particles are moving and the solvent, and then that leads to a slip velocity, and that in turn leads to the motion of these particles. And then on the other side you have the gold, which is then reducing this into this oxygen, into these oxo anions, and these oxygen anion radical then leads as a potent instrument for oxidizing any kind of organic pollutant. So the design was so that you have motion, and then with motion you have reaction, and with reaction you can develop or build in functionalities so that you can oxidize whatever you want. Now you know there are a lot of pollutants which you would like to decompose. So this is one system by which you can do that. So now about the characterization. So these type of materials, when you look for the characterization, you have to look them across in the electron microscopy, and here you have the electron microscopy together with the elemental analysis. So what happens is that you capture the radiation from the material, and by which you can find out the nature of the elements which are present. And this is how Amabrita was able to show that you have titanium, molybdenum and gold, and these were shown in this kind of systems. And then you see what happens, for example, when you have motion in these type of systems. So you have a beam of light that is coming across. So this is visible light, and with this visible light you have the creation of a hole and an electron, because in the valence band you have the hole. Now this hole will split water into oxygen and protons and the reducing equivalents. And then the electrons are then in the conduction band, and then you can have a coupled redox process that can go on in this bandage, in the conduction bandage. So what happens? MO7 or heptamolybdate has empty orbitals, and it is very easy to get MO7 reduced. And how you see that? Because if you reduce MO7, there is a change in color. And so what was happening was these electrons were injected into the MO7 and it was becoming colored like blue. And then with exposure of air, it comes back to the unreduced MO7. And on the other hand, with the gold and on the surface here, you could get this oxygen reduced into oxygen anion radical, which is then really like a potent like a bomb kind of a thing, which can break any organic molecules that it comes in its contact, right? So then what happens when you have the organic molecules which are in the contact, they are broken up, and they are broken up into their non-toxic components. And that's how you can degrade any kind of toxic materials over there in the reaction mixture. So the idea is very simple, that what Abaprita had and we had is that you take these type of nanoparticles in a bottle, right, and you add it to a polluted region, and then it moves, it cleans up the system, and then you can recover it. So that's more or less the idea of this active matter, which are quite potent for doing these type of systems. And I would also like to mention you here that these type of active matter systems were first pioneered by George Whitesides, who came up with two component systems where you have one component that was creating gas, and that would then in turn propel these type of nanomaterials. So, and in this case, what we are trying or what we are doing, we are taking three components together. We are taking the orophilic interactions, we are taking the oxometalate interaction, and we are taking, of course, the titanium's photomagnetic properties. So this is a combination of these three properties which we are using in getting these things done. And you can see, for example, the motion of these nanoparticles, as you can see them moving, and this is the direction of the motion which is shown with you. Now, it has a responsiveness with the intensity of the incident light. As you have more and more of this luminosity, then you have higher and higher mean square displacements of these particles. So this is really like you control the intensity of the light and you see a change in their velocity, and that we can capture it with the diffusion coefficient, and you can capture these diffusion coefficients from directly live from the systems which are undergoing reaction under the microscope. Now, later on, we combined forces with Professor Ronojoy Odhikari, and then we were able to map the solvent force field, meaning that these particles are moving, but there is a turbulence in the surrounding solvent medium. And this turbulence will create some force field which will then propel your particles further. So this has been done really with ab initio type calculations, which is complex hydrodynamics, and Ronojoy is now in Cambridge University. So he and his student Abhrojit Lashkar, so they did the analysis of the solvent medium. So you can indeed map exactly. And what we can also do, that we put some dyes and we could recreate these theoretical patterns which were present under the theoretical calculations. You could see them also with the reaction going on. Now, there were different kinds of systems which we then did. For example, we had SOMs in dithionite. Now, what happens with dithionite is, dithionite can be very good reducing agent. So it reduces the SOMs and then it creates sulfur dioxide. Now, the sulfur can have hydrazine. Now, when you have hydrazine in your system, then with hydrazine you can create nitrogen, right? So you can basically reduce SOMs with hydrazine, and then the nitrogen is created, and this nitrogen then propels these type of systems under the field. Now, these are chemical fuels by which the reaction is made, but you can do also use physical impetus or physical stimuli to do these type of reactions, which I have shown you earlier in the earlier part. Now, these are essentially the mechanical power output, so the efficiency which you can calculate. If you're interested, you can have a look at this calculation, but I will skip it. So essentially what you can see, that the efficiency is relatively high in both hydrazine and dithionate, and there is an optimum concentration where this efficiency is maximum. And this happens because beyond a certain concentration, you have the logging of the gaseous molecules on the active site surface. So that's why you cannot have motion anymore. So there is a drag that is created if too much of the reagent is present. So you, and on the other hand, if you have too less reagents or chemical fuels, then also the reaction is very less. So that would lead to low velocity nanomotors or micromotors. So that's why you need to see an optimum condition where you have this optimum velocity for these type of SOM based active matter. Now, I don't know if this works, but this is a video, for example, where you can see the light. Moment you make the switch on the light, this particle will start moving. Yeah, it works. So you can see it starts to move. And when you have these lights on, it has a directionality. And then when the light is off, it then immediately, almost instantaneously stops moving. And whatever motion you see is basically a diffusive motion. So it's not no motion anymore. So on one side, you have the motion, then again you switch on the light, again it starts to move, again you switch off the light, again it stops. So we have done these lights on and off periodically so as to show that you can induce this motion. And in course of this motion, what we have also done are to decompose some organic pollutants like lacrimeters like benzyl bromide and so on and so forth, which I will show you in the next slides. So basically, the moment you have the lights off, it immediately switches off. So that means you have a clear trigger by which you can do this type of controlled motion of these SOM based nanoparticles. And it's a what we called, or she called, a recyclable motion with on off modes. And you have seen it. So 0 second, 10 second, 20 second, 30 second, like that you can do it. And what you see, the velocities, if you would analyze the velocities, you will see a sharp and an immediate drop from the on mode to the off mode, then again on mode, then again off mode. So it's quite clear and quite obvious in these type of systems which have then immediate application. And this is the application. For example, the simple thing what we did was this methylene blue, which is a dye, right? It's a very simple application. So we had put methylene blue, and then this is the blue color, as you can see, and then immediately after 10 minutes or so, the color bleaches out. And you see, after 20, 25 or half an hour, you can remove the dyes completely from your system. Now, this is particularly important because you know that there are a lot of industrial grade paints and pigments which are left then in the moving water, right? So this is a very facile way by which you can put these type of active matter and you can decompose the toxic industrial waste containing these type of pigments or dyes directly over there. Not only did we do that, she also worked with the degradation of benzyl bromide. Benzyl bromide, in fact, decompose benzyl bromide into benzyl alcohol. And benzyl alcohol is fine, and a little bit of benzaldehyde. So you have this situation where you have these moving particles with a particular specific use in mind that can translate, or that can be translated to some nice new applications. Now, the next thing what I will talk about you in the context of catalysis, this was done by Shuntu Das, where we made, or he made, a polyoxometalate, which was tungsten, copper, and phosphotungstate containing polyoxometalate. So it has a cap, as you can see, two caps, and a belt in between, and these are all crystal structures, and which are then connecting these two and forming a banana kind of a molecule, right? And what was observed is that with these ones, when you put them on reduced graphene oxides, if you put them on there, then there is a direct oxidation of water into oxygen. So this was quite a nice system, and we observed it, and the design was inspired by nature because we put in some manganese in there. So manganese is oxidizing in itself, so that's why we put in some manganese containing units over there, and then to oxidize these systems. So here, for example, you can see that this type of clusters, the oxygen only with the cluster, pure cluster itself. That means if you are doing a homogeneous catalysis, homogeneous water oxidation reaction, meaning you are only using the molecules for the water oxidation, then it's much less inactive activity. But when you make it a SOM with the graphene oxide type interface, then the activity increases. And here also you see a situation where the pH dependence is quite interesting. We see a maximum pH of around 7.5 where the oxidation is maximum. Now, why you need 7.5? Because if you look at the water oxidation reaction, the basic reaction is water going into oxygen plus, so if you have two molecules of water, then it goes into one molecule of oxygen, four equivalents of or four protons and four electrons, right? That's the balanced reaction. So that means if you have a pH that is high in nature, then at high pH the protons are captured, right? And that pushes more and more the reaction equilibrium towards the right hand side. This is simple from the La Chatelier principle. So that's how at higher pH you will always have oxidation reaction. Water oxidation reaction is favored at higher pH, right? But why then, you would ask, that it should monotonically increase? Why is it decreasing then? It is decreasing at even higher pH because of the fact that you have a decomposition of the oxometalates, because oxometalates are mostly formed by condensation reaction, as I have talked to you in the last class, right? So you have metal, oxo, metal, this type of bonds, and if you have more and more of OH minus, then you will have the breaking up of the metal oxo metal linkage, because one hydroxide will come and it will attack one metal center, and then it will open up the MOM type of units. So that's why when you go beyond a certain pH with most of the polyoxometalates, it will decompose, and that would lead to the lesser and lesser efficiency. Of course, there are some polyoxometalates which are very, very stable, like for example the Preissler type anions, which have a ring-like structure. Those are very, very stable. Those are based on tungsten and so on. But anyway, so just to tell you that you have an optimum condition where you have the maximum oxygen, and then when you cross it over, you have a situation where oxygen production is very low. Now, we looked at it with detailed mechanistic from detailed mechanistic aspects, and what we also found is that in addition to water oxidation reaction, this you can have a look at it, this is very standard, but what I would like to draw your attention on to is that if you have a condition where in addition to water oxidation reaction, you have water reduction or you have production of hydrogen, and that was quite interesting. But then at that time we were a bit late with the development, so we thought that we can do it in some other ways, because we are creating reducing equivalents here, right? So photochemically we are oxidizing water and we are creating reducing equivalents, and that's how we moved on to these type of systems. So instead of focusing on water oxidation or pure water reduction, we moved on to this type of situation where we create these SOMs in excited states, and then when it comes back to the ground state, it will emit then the exciton, hole and an electron. Now the hole will then do the water oxidation as we have seen in the last part, right? And the reducing equivalence which you are generating then is injected to CO2, and this goes on to creation of formic acid. So which is quite nice, and at that time it was one of the earliest ones, and the turnover numbers were really high. It was around 1.4 million. So which is quite an efficient and a scalable system. But then later on we thought, okay, it's fine, can we pinpoint it even more? So then it was work again of Shontu. So what he did, he prepared this type of copper phosphotungstate type units. And these copper phosphotungstate type units were created because on one side you have phosphotungstate, which is oxidizing, and on the other side you have copper, which is reducing. So the idea was, can we do it modularly with compartments so that we have oxidation in one compartment and reduction in the other compartment, and we can show that there is a clear coupling between these oxidation and reduction components in these type of systems. And this is what we observed. So we did, of course, the control experiments and so on. So we ran it without CO2. We could not get any formic acid. And then here, for example, the idea was that here also we have the reaction going on at two bandages. So at one bandage, you have the oxidation of water into oxygen, and in the other bandage, you have reduction of carbon dioxide into formic acid. Now, then what we did the reactions and monitored them with GCMS. We furthermore did isotopic labeling, meaning you look at the isotope, you take the isotope, and you take an isotopic carbon dioxide so that you know that your formic acid is coming in CO2, and we could see a shift of around 3 wave numbers. So later on we looked also with the NMR spectroscopy that you have a difference in the formic acid that is produced from 13CO2 and the one that is produced from your 12CO2. So this is what was quite well studied and studied in quite some depths. Now, we also looked at the kinetics of the system, and again, like yesterday, we showed you, sorry, not yesterday, on Friday, we showed you that on the trails, or when you have the chips, catalytic chips, then on those chips, when you do the reaction, they follow heterogeneous kinetics. So likewise, here also, you see this type of sigmoidal curve, which is a result from the cooperativity, and then this is showing this sigmoidal type of behavior, meaning that you have a heterogenized media. So that means the SOMs as the heterogenizing media are the responsible active catalysts catalyzing these reactions. And then we looked at the catalyst loading, and we were able to see that with changing pH, we can get these different types of catalyst loading. And here, what we observed in formic acid, the pH dependence. Now here, the pH dependence is quite interesting because you look at it and you get around 5.5 or around 6. Now, why is that around 6? This is because you want to have a system where water oxidation happens at a higher pH, right? But you are doing carbon dioxide reduction, which is then favored at a lower pH because you are creating formic acid and you have to protonate the system. So that's why an optimum is observed, which we see neither too high pH, not too low pH, but somewhat near the neutral pH, but somewhat acidic pH. You see these type of systems. We then wanted to check that water oxidation is indeed coupled, meaning that you need water for these type of reactions. So then what Shontu did, he did the reaction in dry solvent. so slowly reducing the water content. And then he was able to show that when you have dry solvents, really there is no CO2 reduction. So the reaction stops in these kind of systems. See from the CV that you have a change as you have CO2 adsorbed on the surface, and then you shine light, you are able to see this excited state CO2 adsorbed species, which was slowly showing this decay in the excited state life. And then over here comes water, and the water is used up, and then you over time you can see this intense band appearing, which is showing that you have a reduction of tungsten 6 to tungsten 5. Now this means that you will have an intervalence charge transfer, and that's why you will have color appearing in the oxometalate, and that's what we observed. Then this copper goes into, so this is still copper 2, then it goes to copper 0. So the copper is reduced, and this is the active species. We determined it. This is the active catalyst. So then this copper 0 reduces carbon dioxide to formic acid, and then copper 0 is reoxidized into copper 2. So in this way, we were able to show very much in detail that how this modular two compartments of this molecule reacts even in a macroscopic condition, or not macroscopic, microscopic conditions, because you have these extended forms of structures which are still showing the reaction. Now here I would also like to tell you that we have heterogenized media like these ones, which are useful for obtaining high turnover number, right? That means you can have more and more carbon dioxide converted into formic acid. But then the beauty of these systems is that we have information exactly on single molecular species, and these single molecular species we are well characterized from crystallography, which you are learning in the morning. And then we have the exact structure. We do bond valence sum calculations from where we can calculate the valency of these metal centers. And then we are able to see that how the changes happens in the system from spectroscopy as well as from crystallography. So this is a little bit of application of the knowledge that you are developing in the morning. So these type of systems where you have applied crystallography to get into the application of these type of material systems, right? Now, what we also observed with these type of systems is that they are quite stable. So before and after reaction, it's quite fine. But over time, there is certain subtle degradation, and this degradation we believe is because of the mechanical reasons. We do not think it's because of the decomposition of the component, because we tried to analyze also partly the components which we recovered, but we realized we are losing some of the materials in course of our reactions. Now this was another work. This was done by Soumitra Bormon, who is now a professor, junior professor in GIANxEFAML, Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore. So he developed together with Shonto these MOV9 type systems. And here also what I want to show you is exactly the same type of kinetics you observe. You observe heterogeneous kinetics, you observed oxidation, and you have these type of reduction reactions taking place. Now we changed the system. This is to show you that it's quite general in principle, and then we used this MO 368. This cluster was characterized crystallographically by Professor Achim Müller's group in Bielefeld, and we used these systems, and again here we were able to use it for CO2 reduction in the same way. But here, for example, you can see that the HOMO and the LUMO, you have the two gaps, and you can do the reactions in that fashion. And because of a little bit of time issue which we suffered at the beginning, so I will just maybe condense it a little bit. But what I want to tell you, here we use 13CO2 and we could see the formic acid created with the 13CO2 in there. We can see it from the NMR and we can see it from the spec, from the mass spec. So we were able to see that formic acid created in the system with 13CO2 labeled reagents is different from the 12 CO2 type systems which were there. So, and we were able to see with more reduced products, we were able to see we get also a little bit of formaldehyde, very little, but we still see formaldehyde. That means if your cluster is more reduced, then you have a tendency or you have a chance to get more difficult for more reduced products that are in the system. So, and when we calculated per site turnover, what we observed is that the per site turnover is not that high, it's low. So that means because these are oxidizing, so per metal site turnover was around 6 or 7 units of or molecules of carbon dioxide getting converted into formic acid, which is not bad, but it's not great either. And okay, so these are some of the basic reactions. I skip it like that, but what you can see, it's quite yeah, quite stable before reaction, after reaction, and so on. So this then with this we thought of doing an organic reaction, a simple organic reaction. So we started reducing carbon dioxide to formic acid, and together with that we converted phenylacetylene to acetophenone, and this was a very nice reaction that was done by my another PhD student. Is her name is Joita Lodh. So she did this very nice reaction in the system, and she could show that from the retention times that indeed you have this conversion coupled with the formic acid production. Now, when we realized that you have an intrinsic difficulty with the CO2 reduction with oxometalates because the per site turnovers are low, so we then joined hands with Professor Wolfgang Schöfberger, and this was a work I showed you. You remember I showed the picture also of Shaunik Pal, who was the PhD student who is now in Czech Republic. So he then took these molecules, this type of cobalt corol molecules, and here the idea was with Wolfgang that we said we want to have an axial direction free. Now instead of making it free, he put some triphenylphosphine there. So then the triphenylphosphine will break apart and will give way to carbon dioxide. So when you charge up your system in electrochemistry, so those were photochemistry, now this is electrochemistry. So in electrochemistry, when we put it on the electrode, you have this type of bond which is labile, it breaks apart and carbon dioxide comes in, and then you have the local pockets created where you have these carbon dioxide anions which will couple to give glyoxal, and this glyoxal then disproportionates to give you ethanol. So we were able to form more reduced species. So you see the basic thing is just looking at your systems in detail and then trying to think of ways, but of course looking at the system experimentally is very, very important, and that's what you need to do some nice simple reactions. And with this he was able to get this ethanol at around 47% of Faradaic efficiency, which is really quite high, as I have mentioned you. So this was at the time of production or at the time of publication, this was one of the highest value Faradaic efficiency reported in the literature. And this is what happens. For example, you have stepwise reduction of cobalt corol, and you can see that it comes up and then it goes flat straight into the pocket of this porphyrin ring, and then there is a dissociation, and then this molecule goes away. You have free access of carbon dioxide from here to here. So this is the plane of the porphyrin ring, right? So we are showing it from side views, and then you have the CO2 coming in, and this is then getting converted into this ethanol. We have put here the table so you can see that how these systems are taking place. And with in situ operando IR spectroscopy, we were able to show how stepwise you have the CO2 reduction and how you create this type of new carbonyl stretch, slowly giving way to COH and CO single bond stretch frequency. So you can really monitor them step by step in your reaction system when you are doing electrocatalysis. So, and this is the reaction pathway, as I said you. So basically it goes via the formyl pathway. So here you have the CHO minus, which forms this glyoxal, and this then produces here by several steps ethanol. And on the other hand, you have the HCHO or formaldehyde. Now this formaldehyde goes into methanol. So these are the ways in which you can get these products quite systematically, and you can have a control in these systems. But of course, one of the weaknesses of this work is, for example, we still get a little bit of hydrogen because you get some reduction of the water system, so there is slight amount of hydrogen which we don't like. You can do a modular modification, and that's what I will show you here. Instead of instead of cobalt, if you put manganese, then that is more oxidizing, and this will then give you acetic acid. So this was a nice work that was done again by Shonik, just with manganese, and then we were able to get clear systems. And what I would like to tell you, if you are doing electrochemistry and if you want to know whether your reaction is happening or not, what you need to do, you need to do it under argon and run an LSV. And from the LSV, you can see if there is a difference, then you know that there is some reaction going on in the system. And that's what is important to keep in mind. So this is for the quick run. So you do a run, you don't even need to run a CV, you do the LSV, and then if you see a difference, you know for sure that you have a reaction going on in your system. That is the first way by which we test it in our lab, and then you can do mass spec, then you can do control potential electrolysis to see the stable catalytic current or electrolytic current, and then do more and more systematic work. But the first scanning or the first check is via this type of LSV type systems. And what we are trying to do, and I have shown it but not here, in the last class I have shown now Nidhi has already achieved this C3 formation. So, and we are waiting or we are working now for C4 and for higher types of species. Now very quickly I will just show you that how you can do compartmentalization and do the reaction in two compartments. So what happens there is we made these soft oxometalates and then we put in carbon dioxide, and we were able to show that you have carbon dioxide reduction within the cavity and you have carbon dioxide reduction outside the cavity. So you can have both, and we were able to show that within the cavity just the different types of characterization which we have done. The mechanism is also similar. At the two bandages you have this oxidation and reduction, but what is interesting is this one here. So in the internal cavity you see that as you increase the concentration it goes up. That means you have the situation where you have larger cavity, larger and larger amount of formic acid is produced. But then you have the external cavity, where as the size goes up, your product goes down, and this is very typical. That means when you reduce the size, your product goes up. This is a basic principle of nanocatalysis, where you know that if you reduce the size, you have more and more active sites, and that's where you have more active catalyst. And we were very happy to see this effect in this type of system. So this was a work which was done by Kaushik, who is now in Germany working as a postdoc. So with this, I hope that I have been able to convince you the reaction. So basically the partitioning of the reaction media, and how with partitioning of the reaction media you are able to do reaction modularly inside the cavity and outside the cavity, and you can show that inside the cavity you have the effect of nanocatalysis and outside the cavity you have the other effect. So I hope that with this we come to the conclusion. So what I have shown you is the framework of these SOMs, where you can do partition, reaction, motion, and harvesting the motion by assembly and disassembly. And now we are also able to create reactions to harvest energy. So with this I conclude, and I'll be happy to answer your questions now or later, whenever you have. Thank you. And these are some journals where I serve in the editorial board. So if you have nice work, please do send it over to this GMM. It has now picking up with the impact factor, and of course in Frontiers in Chemistry. So I think we are running a little bit late with the time, but now it's quite fine. So I think 3 o'clock. So without much delay, I think maybe Professor Haldar can give his lecture. So if you want, we can take maybe, I don't think you have question. Okay. Okay, yeah, please. Please, when you ask question, you introduce yourself and then ask the question.
Sir, my name is Musfika Khatun.
That's very nice question. Thank you. Okay. So, oh, yeah, one more question.
Good afternoon, sir. My name is Pooja Kallas and I'm a student from Calgary University. And my question is, in one of the slides you showed that using diethionate, the efficiency increases, and using hydrogen, the efficiency is comparatively less. So, sir, what is the chemistry behind this? Why is it so?
Yeah, that's also a very good question. So what I showed, you have also very good eyes. I did not mention that, you saw it, so that's why you said it. So yeah, that's a good question. So we think it is the efficiency of these agents as reducing agents. So that means the ease with which dithionite can transfer electron and the ease with which hydrogen can transfer electron, these are different. So these are lower. So basically you have more efficiency with one than over the other, and that comes from their redox behavior in water. So because we are doing all the reactions in water, and what we did then, we did a simple titration kind of thing, redox titration, right? And we saw that we have this reducing agent, or Opabrita saw this reducing agent, their behavior, their capacity to reduce is different. So then we switched to light. So or she switched to light, because then you have the much higher reducing power with the luminosity of the system. A very good question.
Thank you, sir.
Thank
Thank you
you.
so much.
Thank you. Okay, so with this, if there is no more question, thank you again, and we will move on to the next lecture by Professor Haldar. You can take a 2-3 minutes break and then switch on with the next. Thank you. Thank you.